A revamp can fail long before the first new module is installed if the plant cannot separate a real constraint from a temporary operating condition. In an aluminum extrusion line, the losses rarely come from one obvious fault. They build across billet heating, hydraulics, controls, cooling, handling, maintenance routines, and changing production demand. That is why the first decision is not which equipment to buy. It is where the line actually loses availability, where it consumes utilities, where quality drifts, and where operators have learned to compensate for recurring weakness. The starting point is evidence. A useful baseline has to be tied to a defined period and a consistent production context. Energy per unit output, planned and unplanned downtime, stop duration, repeat fault modes, scrap or rework, maintenance effort, and operator interventions all matter. A total downtime figure alone is too blunt to guide investment. It cannot distinguish a brief nuisance alarm from a recurring failure that disrupts an entire production sequence. That baseline also has to separate production mix effects from equipment effects. A line may look less efficient simply because it is running more difficult products, shorter orders, or a different alloy condition. The comparison must be transparent enough that the upgrade is judged on comparable operating conditions, not on a before and after story that quietly changes the assumptions. Once the baseline is clear, the line should be treated as a connected process, not a set of isolated machines. Billet heating shapes the condition entering the press. Hydraulic stability affects press response. Cooling and puller coordination influence downstream flow. Stretching, cutting, stacking, and logistics decide whether profiles keep moving without damage, delay, or manual workarounds. The most expensive loss may show up in one place while being driven by another module or interface. Energy and reliability should not be managed as separate projects. A poorly controlled heating system can waste energy and create unstable billet condition at the same time. A hydraulic problem can increase energy use, load maintenance, and reduce production stability. A control upgrade may improve fault visibility without reducing utility consumption directly. Each intervention needs its own value statement. Before any module is replaced, the failure path should be traced from the first visible signal through the response sequence to the production consequence. A puller interruption, for example, may be tied to cooling behavior, control timing, profile handling, or a downstream cue. The point is to find the intervention that changes the underlying condition, not just the component that makes the problem visible. A staged revamp is the most practical way to improve the highest impact constraints without forcing an unnecessary full shutdown. The sequence should be based on safety, production risk, energy burden, technical dependency, and the installation window that can actually be supported. That means audit work and data quality first, then controls and diagnostic visibility, then targeted mechanical and thermal work. Work that changes a control interface may need to happen before a mechanical replacement. Work affecting shared safety circuits may need a wider review. Heating upgrades should be judged against the billet range, transfer sequence, sensing approach, thermal uniformity, and real operating schedule. Hydraulic and drive work may address where leakage, heat, pressure stability, response behavior, energy use, or maintenance access. Downstream changes need the same discipline. Cooling adjustments can alter puller timing, handling changes can affect stretcher availability, and a saw or stacker change can create a queue that reaches back to the press. Automation belongs after the process logic is stable. If the alarm sequence, material handoff, or recovery process is already unclear, automation can make the confusion harder to diagnose. The plant needs a defined normal state, safe stop, fault indication, restart authority, and evidence that the system has truly returned to normal. Commissioning should then be treated as a controlled evidence event, with representative production conditions, recorded stops, alarm behavior, utility data, quality observations, and the remaining actions before acceptance. After the upgrade, the comparison should return to the original baseline, using the same boundary and production context where possible. Availability, stop frequency, time to recover, energy per unit output, quality variation, maintenance effort, and operator interventions should be reviewed together. The result needs to show both the improvement and the remaining limitation. That is what keeps a revamp grounded in operating evidence instead of broad claims.